Hi, welcome back to Mrs. Thompson's classroom. Today we're going to define integration as the limit of a sum. So in the previous video we talked about Riemann sums and how we found the area by adding up all the little rectangles. Well, if we take the limit of that summation, letting the number of rectangles go to infinity, then we can get the exact area. So before we start doing that, we need to review just a little bit about sequences and series. So a sequence is simply a list of items. In math, of course, we're going to be doing lists of numbers, and they tend to have a pattern to them. And A sub n will represent the nth term in the list. Okay? And so you actually can think of it as a function with a domain of the natural numbers. Okay? All right, a series is the summation of the terms in a sequence. And this example here is finite because it has an ending term. We can also have infinite sequences and series. Now this notation, the capital E is called a sigma, and the I is our counter. So we're going to start at 1 and we're going to go up to n. So for instance, in this example, we're going to let I equal 1 to 5. So we're going to plug in a 1, and then we're going to plug in a 2, and we're going to keep going until we reach I equal 5. And when we get to I equal 5, we stop, and then we add them all up. So this is 5 plus 7 plus 9 plus 11 plus 13. When we add those up, we'll get 12, 21, 32, 45. Now, of course, as this top number gets larger, it becomes very cumbersome to add these all up. And so there are some rules. And so the first thing we're going to do is look at these properties. So if we're taking the sum of a constant, that's like taking C and adding it together in times. And so what we end up getting is just n times C. Okay? That's for C being a constant, and n is the number of times that we're adding that up. Okay, we also see that we can take the sequences and add them together and then take the summation, or we can take the individual summations and then add them together. Property number 3 here tells me that if I have a constant times a sequence, then I can pull the constant outside. And then there are 3 rules for either I. This would simply be 1 plus 2 plus 3 all the way to n will equal n times n plus 1 over 2. This sequence is adding up the terms of I squared, so that would be our perfect squares. So 1 squared, 2 squared, 3 squared, 4 squared, all the way up until I get to n squared. And it'll have this formula. And then we even have one for I cubed. Now the reason these are helpful is because now this sequence we were just using, let's say the n value is now larger, and I don't want to sit there and add up all 20 terms. I can split this up. First of all, I can take the sequence of 2i plus the sequence of 3, and that's using this property 2. Okay, and then I can also pull the 2 out front, and that's using property 3. Okay, now these sums are still going from I equal 1 to 20. Okay, now this first sum then can use property number 4 here for the sum of I, and my n value is now 20. Okay, and it's multiplied by 2. And then the 3 is a constant, so I can use property number 1 and simply say that that's going to be 3 times 20. So my end result here is going to be, the 2's will cancel. I'll get 20 times 21. And then 3 times 20 is 60, so we get 480. Now this is going to be useful in helping us define an integral. So let's look at a definition. If f is defined on a function, and we divide it up into a bunch of subintervals, then the integral is going to be the limit of the sum of those rectangles. Now, interestingly enough, this integral, this limit, will always exist if the function is continuous on the interval, or if all it has is a limited number of jump discontinuities. And if the limit exists, then we say the integral exists, and we call the function integrable on that interval. Okay, so let's take a look at how that works. So let's take this function. 3x plus 5 is a line. Okay, and we're going to go from x equals 2 to 6. So we're looking for this area here. Okay, now the first thing we're going to do is we're going to find our delta x. Delta x is always b minus a over n. So in this case, that's 6 minus 2 over n, and that's 4 over n. Okay, and then we want to find that partition, like we were going to do our Riemann sum. So the first value is our a, which is 2, and then we're going to add the delta x. And then we're going to take that and add delta x again. And then we can just keep doing this until we get all the way to the final value of 6. Now you'll notice each of these x values in the list is 2 plus some multiple of delta x. And the multiple is going to be based on the term that we're on. So this would be like x sub 0. And then this would be x sub 1 because I've added it one time. And then x sub 2 because I've added it twice, and so on. So then each rectangle that we would form is going to be our function value times delta x. Well, the function is 3 times x plus 5, and then we're going to multiply that by our delta x. Okay, so our area is going to take the sum of all of those values. Now I'm going to go ahead and multiply the 3 through there, so that'll be 6 plus 12 over n I plus 5 times 4 over n. And I'm going to add this up from 1 to n. Okay, so that'll be adding up all of these rectangles that I have formed. And then if I let n go to infinity, I've now done as many possible little rectangles in here as I can, and I have filled it all in. So let's go through and do a little algebra and see if we can simplify this. So the first thing I notice is 6 plus 5 is 11, and then I'm going to multiply this 4 over n in there, so I have 44 over n plus 48 over n times I. Okay. Now, the n, let's remember, is constant. Okay, I is my variable, it's my counter. Okay, so my properties tell me that this summation of the 44, that's a constant. So that is going to end up equaling just 44 over n as the constant times however many times I want to add that up. Okay, now let's do the next one. This one has an I, and I is my counter. So I'm going to have this 48 over n as a constant, and then I'm going to use the summation formula for I, which was n plus 1 over 2. Okay. Now we're going to take the limit of all of that. Okay, well, first of all, here these n's cancel, and I'm left with 44. So that is not based on n at all, so that will just equal 44. Okay, in this second one, hold on, I lost something. This would be n squared. In this second one, I actually have 48 times n squared plus n. And so my largest exponent here is n squared. And so as n goes to infinity, the rest of the n values are just spit. And so n squared over n squared is going to go to 1 and leave me with 48 over 2. So those are just our rules for an infinite limit. So I end up with 44 plus 24, and that's going to equal 68. All right, let's try this again. So we have this picture. The function is 16 minus x squared. My a value is 1, and my b value is 4. So my delta x is going to be 4 minus 1 over n. Okay. My each value of x is going to be a plus delta x times I. So that's going to be 1 plus 3 over n times I. Now this area is going to be the integral from 1 to 4 of my function dx. So this will equal the limit of the summation of my function times my delta x. Okay, now the x of I we found was 1 plus 3 over n times I. So the first thing I'm going to do is I'm going to FOIL this out so I can simplify my summation. So I'm going to do the limit of the sum. Okay, and I'm going to have 16 minus, and if I FOIL this out, that's like 1 plus 3 over ni times itself. So I'll get 1 plus 6 over ni plus 9 over n squared I squared times 3 over n. Okay, let's continue with some algebra. So I'm going to subtract all of this. Okay, and then I'm going to take this 3 over n and multiply it through. So 16 minus 1 is 15. So I'll have 45 over n minus 18 over n squared times I minus 27 over n cubed times I squared. Okay. Now we use our rules of summations. This first value here is a constant. So I'll have 45 over n times n. The second one, I'm using this value of I, which is n times n plus 1 over 2. And the last one, I have to use this I squared, okay? So the 45 is a constant, so it just stays as itself. In this value here, in this second term, this is n squared plus n, so my n squared are the ruling factor, will cancel to 1 and leave me with 18 over 2. In the end term, I have 2n cubed as my leading term with an n cubed, so I end up getting 27 over 6 times 2. So when I add this up, I'm going to get 45 minus 9 minus, let's see, that would be 9. So that final result is 27. Right? Now, later on, we're going to learn how to actually calculate the integral without using these summations, because we're going to find that the integral is based on our knowledge of derivatives. But we want to really understand that this concept that an integral is an area, that is the sum of all these things, because we're going to use areas to find totals, summations of things later on. Okay, now final example here, let's take a limit and see if we can describe the area. So the first thing I notice is this is f of x times delta x. So my delta x is equal to 6 over n. That is always equal to b minus a over n. Okay, now depending on how I define my function will determine what a is. So I have two options for my function. I can say that it is x squared, and this would give me an a value of 3, because this would be 3 plus delta x I. Now, if a is 3, then I have 6 has to equal b minus 3, and b would be 9. So my area that I have found is actually the integral from 3 to 9 of x squared dx. So it is the area from x equals 3 to 9 under f of x equal x squared. Now there is an alternate way to define this, and that is to let f of x be 3 plus x squared. In this case, the a would be 0. Okay, because there isn't another number there, and so this would tell me that 6 has to equal b minus 0, so b would be 6, and my area would be the integral from 0 to 6 of 3 plus x squared. The difference in this is that x squared and 3 plus x are just shifts to the left of one another. That's what the 3 plus does, is it moves x squared to the left. So we have moved the function, but the area remains the same. So either of those are a legitimate answer for that problem. Okay, so hopefully that gives you a little understanding of what an integral is and how to define it. In the upcoming lessons, we'll learn some properties of integrals and some other methods for calculating them. So hopefully that helps. We will see you next time.